Microgrids, Power Reliability Through Decentralization. This document explores the concept of microgrids and their role in enhancing power reliability through decentralization. It delves into the mechanisms by which localized power systems contribute to a more resilient energy infrastructure, offering insights into the benefits and operational aspects of microgrids. Introduction to microgrids. Microgrids are localized energy grids with control capabilities, meaning they can disconnect from the main grid and operate autonomously. They are typically comprised of distributed generation sources, such as solar panels, wind turbines, fuel cells, and combined heat and power (CHP) systems, energy storage systems, like batteries, and controllable loads. This localized approach to power generation and distribution offers several advantages over the traditional centralized grid, particularly in terms of reliability. Decentralization and enhanced reliability. The core principle behind microgrid reliability lies in decentralization. By distributing power generation and control closer to the point of consumption, microgrids reduce reliance on long transmission lines and large, centralized power plants. This decentralization contributes to enhanced reliability in several key ways. Reduced vulnerability to wide-area outages. Centralized power grids are susceptible to cascading failures. A single point of failure, such as a down transmission line or a malfunctioning substation, can trigger a chain reaction that leads to widespread blackouts. Microgrids, on the other hand, are isolated from the main grid during outages. When the main grid fails, a microgrid can disconnect and continue to supply power to its connected loads, ensuring continuity of service for critical infrastructure and essential services. Increased resilience to natural disasters. Natural disasters, such as hurricanes, floods, and earthquakes, can severely damage power infrastructure, leading to prolonged outages. Microgrids can be designed to withstand these events and quickly recover from disruptions. Distributed generation sources can be strategically located to minimize exposure to hazards, and energy storage systems can provide backup power during emergencies. Furthermore, the ability to island from the main grid allows microgrids to operate independently even when the surrounding grid is damaged. Improved power quality. Microgrids can improve power quality by providing voltage and frequency support to the local grid. Distributed generation sources can respond quickly to changes in load demand, maintaining stable voltage and frequency levels. Energy storage systems can also help to smooth out fluctuations in power supply, ensuring a consistent and reliable power supply for sensitive equipment. Enhanced cybersecurity. Centralized power grids are vulnerable to cyber attacks that can disrupt power supply and cause widespread damage. Microgrids can be designed with enhanced cybersecurity measures to protect against these threats. By isolating the microgrid from the main grid, the attack surface is reduced, and the potential for cascading failures is minimized. Support for renewable energy integration. Microgrids facilitate the integration of renewable energy sources, such as solar and wind power, into the grid. These sources are often intermittent and unpredictable, which can pose challenges for grid operators. Microgrids can use energy storage systems to smooth out the variability of renewable energy sources and ensure a reliable power supply. They can also use advanced control algorithms to optimize the dispatch of distributed generation sources and manage load demand. Operational aspects of microgrids. The reliable operation of microgrids requires sophisticated control and management systems. These systems must be able to monitor and control distributed generation sources. This includes managing the output of solar panels, wind turbines, and other distributed generation sources to meet load demand. Manage energy storage systems. This includes charging and discharging batteries to balance supply and demand and provide backup power during outages. Control loads. This includes shading non-critical loads during peak demand periods to reduce stress on the grid. Coordinate with the main grid. This includes seamlessly connecting and disconnecting from the main grid and exchanging power with the grid when it is beneficial. Optimize energy use. This includes using advanced algorithms to minimize energy costs and reduce emissions. Challenges and considerations. While microgrids offer significant advantages in terms of reliability, there are also challenges and considerations that must be addressed. Cost. The initial cost of deploying a microgrid can be high, particularly if it includes energy storage systems. Complexity. Microgrid control and management systems can be complex and require specialized expertise to operate and maintain. Regulatory barriers. Regulations governing microgrids are still evolving, and there may be barriers to interconnection with the main grid. Intermittency of renewable energy. The intermittency of renewable energy sources can pose challenges for microgrid operation, requiring careful planning and management. Cybersecurity. Microgrids must be designed with robust cybersecurity measures to protect against cyberattacks. Conclusion. Microgrids offer a promising approach to enhancing power reliability through decentralization. By distributing power generation and control closer to the point of consumption, microgrids reduce vulnerability to wide-area outages, increase resilience to natural disasters, improve power quality, enhance cybersecurity, and support the integration of renewable energy sources. While there are challenges and considerations that must be addressed, the benefits of microgrids in terms of reliability and resilience make them an increasingly attractive option for communities, businesses, and critical infrastructure facilities. As technology advances and regulations evolve, microgrids are poised to play an increasingly important role in the future of the power grid.